Okay, I think we'll go ahead and get started. A few people might join us late. It's a great pleasure to have my friend and colleague, Peter Binev, here from University of South Carolina. And he's going to give a talk today on his atomic scale chemical imaging work and how advanced mathematics can bring out information that otherwise couldn't be detected. So,
okay, thank you very much, Kevin. It is very nice to come here to. I'll adjust the camera because I'm taller than I should be. So it's a pleasure to be here in Rice. I've been here several times. I actually was one of the first people to see your. It's not very new, but the new fancy microscope even before it started working.
Exactly.
Very nice. So I was accidentally here, but that was to be. And I'll be talking about processing electron microscopy data. And this is, most of the results are joint work with my former student who is now pursuing medical career, Kelsey Larkin, also Zineb Sagi, who actually collected most of the data, which gave a lot of insights about this, and Toby Sanders, who was my PhD student many years ago, and now he's working in the industry. Still doing some tomography stuff though. Okay, I move this a little bit up. So the first thing I want to talk about is the big data. So when people talk about big data, they say, okay, data processing, we have big data, we have to understand what is happening. However, in electron microscopy, although we collect enormous amount of data there, it turns out that this data is not enough. This data is not enough to understand what is going on there, what is happening. So that's why we have to use models to understand that. We have to know the physics of this data, not just to use data by itself or use some very simple model, but that's why we consider two big approaches: data-driven, which is mostly statistical approaches, which understand the data and try to see the connections between the data, and the model-based, in which you know something about it. You know what is the model behind, or probably you don't know it enough. You have to actually adjust the model based on the data. And the most important things are, I put that reliability is the first one. How reliable are the results? How stable are the results? And then the efficiency of computations. And because every day now we are talking about all these deep neural networks and something like this, they lack of all of them, except maybe efficiency in some cases. But anyway, we have to do something about this. And the big data usually emphasizes on efficiency, how to process this data. And in electron microscopy, there is probably some point in considering the big data problems, because we collect a lot of data, and sometimes the channels are not wide enough to push this data through and to record that. So we often have to compress it before we extract it from there. And these processing algorithms are very interesting, but that also reflects the way we are collecting the data. So I will talk about something which we call small data, or usually it's known as data poor situation, in which the data is not enough to understand the physical process completely, and we have to bring some additional knowledge, something we know from other experiments, in order to get what we have to do. And the thing is to combine the two approaches. From one point, to have a very good data processing techniques, and then from the other one to learn the models and to find the proper models which are applying to the data. So I will consider data from scanning transmission electron microscopy. I want to say something about it. What is important there? The important thing is the scanning. This collects information by scanning, actually pixel by pixel, and this creates a lot of issues. The other thing about electron microscopy is that because actually organizing the data gathering process is very complex, and actually making this electron beam concentrated enough is a very expensive process. We don't want just to collect one piece of information based on this. That's why people usually have a lot of devices to collect different information. You can talk about dark field, bright field, which are kind of the basics, but usually people collect yields, which means how much of the energy of the electron beam is taken out when it goes through the material, or EDX, which means, I'll talk about EDX in a bit. So just to give you an example about how important are the models, I want to say something about a typical problem in STEM. So the usual way we understand data is to say, okay, the data, we have this additive noise. Sometimes people could consider multiplicative noise. This is Poisson type noise, which is similar to that, so I will not discuss it. But the important thing is that usually when we consider this is the sum or even the product, this is kind of the linear model. This can be linearized easily. But if you cannot, if it is very nonlinear, then what should we do about it? So usually the problem in STEM is the position noise, because you attempt to take everything from different, the information from different positions, but keep in mind that these are very small spaces. A nanometer is a very big distance there. So you move it, and then, of course, you cannot expect that the current from the electrical system would be absolutely steady, and that means that the magnetic field will be absolutely steady. So there are some small fluctuations of it, and that creates this position noise. And the position noise, generally people have drift, which means this is usually the inertia you actually introduce when you're putting the probe into the viewing place. Because usually I say an inch a day speed is very big. It can destroy your experiment. So that means if it is moving a little bit, but the drift is not a problem because this is near linear motion, so it can be extracted and can be taken away. The problem is the jitter. The jitter comes from instability of the magnetic field, which actually positions the beam. And that's why it is nonlinear, very chaotic. There is no way to describe it, but we have to take it out. And as I said, that usually the microscopes are good enough. They are very well shielded. Everything is done with care to not to introduce this additional noise. And usually in a nanoscale, you don't observe very bad position noise. However, if you go to atomic scale, that means an angstrom or even lower, then you can observe a lot of jitter in the experiments, even the best microscopists in the world, with the best microscopes, they cannot avoid this. So and then the effects of the position noise, they actually dominate, and the inconsistency, the high resolution images are not very precise just because of that. And that means that the position noise theta should be removed and estimated. So how to do that? You cannot simply do the same experiment and say, okay, we'll find a way to introduce this just using mathematics. You have to change the experiment. And the way to change it, which was used before just for purposes of kind of averaging the results, you take, instead of one, you take several different scans from the same place, from the same position. And when you do that, you practically repeat the experiment. Supposedly, everything is in the same positions, but the positions are not the same. And then you can eventually estimate the movements. Of course, it needs a lot of mathematical insight and everything to do that, but it's possible to do that. And then with several others, we have achieved, probably that was 7-8 years ago, the best precision measurements of the interatomic distances. And that means not interatomic distances for kind of regularly spaced atoms, which can be done much better because of the repetition. We're talking about when there are some defects in the atomic structure. So if we don't have the perfect lattice, then this is the interesting case. When what are the distances there? And we kind of consistently have established that the distances we measured are below 1 picometer. The previous results were about 3 to 5 picometers, the best possible results. So we did that. Why? Because we did the proper model and the proper acquisition process. So just to say something about this, this is kind of the position noise we detect for one sample. This is from that paper. And you can see this is the drift, the general drift, and the jitter is inside. And this, of course, it's kind of only presenting a vector field. This green window here, if it is expanded, it has much smaller drift, the general drift. This is the general position. And when you subtract this drift, you still have everything is going in different ways. So that means because the probe is scanning, we cannot expect a lot of changes in the position, but then this still happens. Okay, now let's go back to energy dispersive X-ray spectroscopy, which is usually I call it EDX because that was the way I was introduced to. I'm a mathematician. I'm not doing anything in material science. But several people put it EDS. It means the same. Simply instead of some people even put EDX S. But so what is the phenomenon? You have your sample. You have your very well concentrated electron beam, which is going through the sample, and then it disturbs some of the atoms. The disturbing, that means you're investing a lot of energy there. So some of the electrons in the atoms, they got kicked out by the direct hit of some of the electrons of the beam. And because they are kicked out, if they're in the low orbit, usually the electrons from the higher orbits, they try to compensate. They go to the lower orbit. And when they go, depending on whether they go from the L shell to the K shell, or from the M shell to the K shell, or from the M to the L, or there is an N shell also, it's simply not in, that is from Wikipedia, some way to show. So what they simply, this electron which goes to lower orbit, because of the certain number of the positrons inside of the kernel, we have very specific energy to go from one orbit to another. And this energy is well investigated, and people know what is that energy. And if you detect that energy, then you know what is the atom. So it's different for different atoms because they have different number of positrons in the middle. Of course, if you consider these tables, they are very complex, but these are usually the processes which are very, very well known, and that is the way to detect what type of atoms you have in your sample, exactly where the beam is going. When you move the beam, you get something else. The problem, the data poor regime, is the basic reasons for that is that you have to consider very small amounts of X-rays. If you want to have a lot of X-rays, probably you wouldn't have a material at the end. So and keep in mind that this is usually very small. So this is a typical example. This is 6 randomly taken pixels. You can see this is this usually the smallest one is detecting just one X-ray in the specific energy level. There are several energy levels. There are in this particular experiment, there are 4,000 different energy levels. Each one is about 5 electron volts. And they are from 0 to 20 kilo electron volts. And then when you get this, you get different concentrations. And when they concentrate on the specific place, you say, okay, this is probably about some of the energies which I want to which I can assign to certain atom, and that means it shows that there are some high concentrations of these atoms in this particular portion of the sample. So that is what we do, and then what is the EDX doing? This is we're concentrating the electron in the specific spot. We call it pixels. In the each pixel contains a vector of 4,000 different energy levels, and on each of them we detect how many X-rays we detect on that. So the thing is that, of course, these X-rays should be captured, and I think that nowadays are probably they have detectors which kind of cover about 10% from the total. I mean, you can see the sphere around the probe, and then you can capture it. About 10% is considered a lot. Now, the usual detectors, they have from 2 to 5% of the total X-rays. That means even if you cannot produce a lot of X-rays, you can capture only a small amount of them. Then the thing is that actually these energies, we know that the expected value is something, but usually it's spread around as a Gaussian, and this is also kind of a problem. It doesn't go to one and the same place, it goes to nearby energy levels. And then these Gaussians of different atoms, they sometimes overlap. There are atoms which have very close energies, and then you cannot recognize which is which. So the goal is to get something, and then you have this background noise or background signal, or I actually change it to baseline signal. I was told that this is the proper terminology there. And as I said, we're in the data poor situation. So deep neural networks are not very useful for that. They could be useful in some cases, but because we emphasize on reliability, because of the small numbers, we cannot be sure that we collected enough. So this is to show how many X-rays we collect per pixel. Keep in mind, one pixel has 4,000 different tabs, and the total number is less than 700. Actually, it's mostly about 200 and 300, and in the empty pixels is a little bit small. So now we want to use the tomography. So we want to use the EDX tomography, which means that we observe the same probe from different angles. And when we observe that, we have to be very careful with the energy we invest in the process, because we don't want to destroy it at the end. So that makes it very small amounts of pixels. So this particular experiment is about 200 by 100 pixels. And we have 37 tilts. So it is the full range. I'll talk about this a little bit later. So we collect it. It turns out in the whole experiment we have about 200 million X-rays, total of X-rays detected. But these X-rays mean so much, so there are very few in place. We're interested in the concentrations of 5 chemical elements, and there is a copper also there, which I'm not interested in, but it's very everywhere. And we have to take care of it. So that is, for the experiment, we have this particular spectrograms. This is the combined spectrum of everything, which indicates certain places. So these are called peaks. Usually we have here about, we have identified 11 peaks, and you can see that some peaks are very near. These are nitrogen and oxygen. Actually, we also have 2 very close to each other. These are relatively close. But they can be separated. These are also close enough, and they interfere with each other. So what we do, we consider the domain of the pixels. We consider this P, which we have, and it goes to the range. And then if we consider this kind of function and try to learn it or make a tomography of it, it's absolutely impossible. We have way too few information to be able to actually decide to make a tomography reconstructions based on the entire spectrum. So we have to set for something small. And this something small is to say, okay, we are not interested in what is the spectrum to make a tomography reconstruction of the spectrum. We're interested in making tomography reconstructions of the quantities we are interested in. And what we're interested in is what are the concentration of the chemical elements. So we want to have a function which takes us from the spectrum for these 4,000 elements and to give us information about very few concentrations. In our case, these are just 6 elements. Unfortunately, these 6 elements don't show only in 6 places. They show, actually, these ones are showing on 12 places. So we have to combine the information from them. But at the end, we want to resolve a situation in which we are not working with Z to 4,000, but with R plus to the 6. So that means this is kind of the compressed sensing of it. We want to compress the information into few, and the thing is how to do that. And the standard solution is the following. They say, okay, each of the atoms have specific intervals in which it shows up. In some of them, it doesn't show up very much. They choose the primary interval usually. they have this interval and they collect all the information from this. And this is fairly good. If you are able to determine where exactly is this interval, because keep in mind, theoretically, you know what are the energy levels between which we have to collect, but your detector probably don't detect this exactly. There could be some shifts, so there could be some interference. You have to deal with that also. But that is the standard way. This is what the standard software for the microscopes. They come with this software, so you can immediately detect these concentrations directly from there. The bad thing is that if your concentrations are not very high, that will not be very helpful for you. Our solution is to have a learning routine. I'll explain this learning routine a little bit later, but basically the idea is to say, okay, can we learn which are this transform from Z to the 400 to R to the 6 in our case? How can we learn it? And as I said, deep neural networks are not good enough yet for that. They could be a little bit more reliable. Okay, so I want to say something about this. This is not the experiment I'm talking about, but because it's a little bit more eventful, I want to say what is that. So this is the combined spectrum. This is the measurement. This is for the entire experiment, which has, I don't know, this is in terabytes, what was collected information. But it has very few X-rays detected. And the total X-rays, it is around gold. This is gold here. This is, I frankly don't know. This is either mercury or gold because they are very close to each other in that position. This is gold again, and I think it might be cadmium, this one. It doesn't matter what that is, but this is the information we get from all the entire spectrum for the entire experiment, which was a little bit more than 12 hours in time. And we get this function. From this function, we have to say, okay, which are the basic functions, I call them modes, which are there. So you see that this is the baseline signal. This is the noise. Practically, this is information that is not useful. It contains actually here another element and probably another element here, which are very, very much traces of that. But we have a significant amount of presence of gold because gold is there. We have, in this position, we have another one, and then we want to know what is happening. So the basic idea is the following. If we have that, how, as mathematicians, we say, okay, what we want to learn, we know the biorthogonal filters. We want to filter everything else and to keep only one. So we consider these 5 modes and say, okay, we know that we can think that this, what is happening here is kind of the expected value. This is approximate expected value. And we wanted to have them biorthogonal expectations. And these are the biorthogonal spectra, biorthogonal filters, which should be applied. And then when you apply to individual X-rays, you can say what is most likely result for this. So what is the most likely concentration for that? So this is what is our methodology. You can see that actually you can make hands-on approach, but this is a little bit better, and that actually these biorthogonal filters gives much better. For that, I want to mention that the experiment was made by the group of Sarah Hyde from Manchester, and it was processed by my student Gillian Garzarella. Now, what are the problems which we face? Because we say, okay, we investigate the spectrum and then we make our decisions based on the combined spectrum. So this is the spectrum for our data, and different tilt angles are with different colors. You can see that they almost overlap everything. There is small fluctuations here and there, but this is not essential, so they show the same. This is the SARAS data, which was taken out of from angles from -60 to +55 tilt angles. And you can see that -60 has much more energy because it was, the first example is when the probe is kind of a rod, and we consider this rod. The second one is a slab, and when you go for big angle, the zero angle is this. It's usually very small interaction. When you go to the big angle, you have much more interaction. But there is a lot of absorptions in this. And the absorption, you can see that it is usually the absorption H here somewhere about 9 kiloelectron volts is the absorption by copper. And here you can see that the signal goes up and then it actually drops almost one level of magnitude. And you see different things, but this doesn't worry us too much because we are considering the local spectrum. What worries us much more is that you can see the green line is almost flat here in this region, and you definitely can detect a lot of things are going on. So there are some chemical elements which are probably absorbed, or I don't know what is happening. So that means if you consider sometimes if you have a bias in certain direction, the obvious bias is the tilt direction in this case, and you have to treat different tilt directions separately and to consider the things separately. That's why I said that the second problem is much more difficult. So the generic algorithm of what I'm talking about is so we have to do the combined spectrum and then to identify which elements are there. Usually, if we have additional knowledge about the microscope and all the things, we usually can have this information about that. We can identify what types of the Gaussian light peaks and then easily determine that, but we have to have some mathematical way to process this information for each particular experiment and to make sure that we have the proper parameters when we proceed. And then after, we have to make a procedure for calculating the number of X-rays which are related to certain elements, to extract the element maps of all tilts. And when you extract the element maps, this is the standard tomographic reconstruction. If you have been to the CT scan somewhere or the MRI or something like this, you have seen it's different here. The difference is that in MRI, they put you somewhere and they turn you around. However, when they turn around the sample in the electron microscope, it is not on focus anymore. They should recalibrate the microscope, and that means they are changing the position. Actually, it's amazing that they get about the same place. So you have to do the alignment procedure, and this is we're using this paper, which actually have calculation of the local centers of mass, which are very useful for that, and they see how they move, and they want to make it to move in a circle, because when you tilt, the center of mass should go around, and you have to align it based on that. And the tomography reconstruction is made by my former students, Toby. Okay, I'll talk a little bit. So the composition of the spectrum. So the spectrum, we detected 11 peaks here. These are different colors. Some of them interfere, they have to be processed together. And then we have this baseline signal, which actually, in this particular experiment, because we don't have a lot of absorption there, can be approximated by decreasing convex piecewise linear function, which is here. There is a little bit of absorption here, that's why this kind of doesn't appear very well, but this is good enough for our experiments. So the next thing is to say, okay, we have our signal, we have the noise portion, which we have the baseline signal plus some additional error component, and we have the linear combination of the peaks. So if we want the thing which we want to know are these coefficients Cj. So the thing is how to calculate the Cj's and how to do that. So, and in this particular experiment, although we can do it differently, we kind of calculate that as a difference between the whole signal and the sum of the G's. So, okay. Now we consider this. Now how we these are the standard Gaussian representation. Probably, if you study statistics, you can say that we have a 2. It's a nuisance to get a constant 2 there, so that's why we didn't do it. But the most important thing is that the things which we should know, the Cj is the estimated things. In order to make the model, we need the knowledge of the centers Xj and the sigma j. It's not a standard deviation because we don't have 2, but these are the 2 components. The sigma j talks about the spread. The problem is that the instrument gives you different values of those, but sometimes also we have different phenomena. Sometimes the energy level, and this happens quite a lot, of the same chemical elements are very close to each other. They kind of make 2 Gaussian peaks, and then you have to combine them too. We don't want to write another models. Actually, we experimented that, making the sum of 2 Gaussians and try with different coefficients and try to mimic that. It's almost impossible to do that. We need a much bigger database to do that. But then we can consider that we kind of slightly enlarge the sigma j. And then it turns out that actually, especially for lower energies, the sigma depends actually on x. It's kind of extends a little bit towards the lower energies. And that's why we have to, we can consider this. For our purposes, this one is good enough. So in a sense, we detect the sigma j, although we have to enlarge it in some cases. But we do that from the experimental data. This is kind of adjusting the model. And this is what, so I now go fast over the experiment. So what we did first, we detect where the bumps are, because when you start detecting this is kind of discrete data. It's not smooth. So basically, we have to, if you consider this peak, it looks something like that. You can imagine that this is the basic region, is the concavity region here, and it's good to detect it. We cannot, that is, the second derivative is negative. we cannot calculate derivatives. That's why we use center of mass displacement. What is center of mass displacement? We get some small portion of the spectrum and then calculate, we have an interval and we know where the center of the interval is. And then we calculate what is happening with the center of mass when this function is considered. And then the center of mass of the function, if the function is increasing, will push in this direction. So we will have a displacement which shows us that we are in this portion, and then on the other portion it changes. So if we actually analyze this displacement, we can say where these intervals are without taking derivatives. So that is fairly robust method, and it actually detects a lot. And then whenever we calculate, we also calculate the significance of the peaks. The biggest peaks have more significance because they can interfere eventually with the nearby ones. So we take the first one, we extract it from there, and then from the difference we calculate the second one. This is this one. Then the third one, it appears to be this one. It has more, so the way we calculate the importance, it has more importance than that one. And so on. We can do for all of them, and we collect these 11 peaks. And then we approximate them with Gaussians. So these are the approximations. Here, the third one is missing for a reason. So these are the L line, K line. That means that this is the line for the missing electron, which is replaced. And if you have alpha, that means it's coming from L. If you have beta, it's coming from M shell. So that is kind of the language which is used there. But you can see fairly good. These are a little bit off, this one, simply because there is another peak next to it and it cannot be approximated. We further approximate. This is just an initial. I will not show you the pictures because they are almost coincide. Further, we use cycle spinning we use Newton's method to find the better thing, and then we extract every other all the other peaks except the one we approximate and do that. It's very good. However, we have this situation here. This is nitrogen and this is oxygen, and you can see that we cannot approximate them very well. And the reason for that is that actually there is a titanium peak in between, which is very small relatively, and it cannot be captured. One way to capture it is actually to decrease the points. We are using all these points to approximate. If we decrease the points, if we have only the points starting from here, so then to make the approximation, we get this beta, which actually better reflects what is happening, but we're not doing that for this particular experiments. We do something else which is much more interesting. So this interesting thing is the following: because we know that we have titanium, we actually detected titanium in this. This is the biggest peak for the titanium. And we know that it should appear somewhere here between the nitrogen and oxygen. And when we do that, we say, okay, why don't we subtract this? If you see that these are all the detected pixels in which they have no emissions between these two energies, which are exactly where the main peak for the titanium is. And if there is nothing, you see that the field changes. So this, which is aluminum, is missing here. Why? Because the titanium and aluminum in these samples are going together in the same places. The others are much more diminishing because this one gives almost 3, an average of 3 X-rays per pixel for all the pixels. This one, the average is between 0.7 and 0.8. That means but it's still a very big sample, and the most important thing about this sample is that here the oxygen and nitrogen are very well separated. So we can do a better approximation of them, and this is from this missing titanium samples, which we can calculate the nitrogen and oxygen peaks. We calculate them. After we calculate them, we calculate their characteristic, the xj and the sigma j for them, and then calculate only the constants to make the to separate them from the entire spectrum. And then this is what is the remainder. In the remainder, when we consider it, it is this function here, which actually, if it is amplified, becomes this one. And we detect actually two elements. This one is the titanium. This one happens to be the calcium, which we can extract. And when we extract the calcium, actually, we can see that some small amount of carbon is also available there. However, both this calcium and carbon, we consider them part of the baseline noise. So just to extract them. So, and based on this, we can consider the peaks which are nearby. We have to consider together, and we have 12 significant peaks, adding this titanium here. And then we can spread them into different intervals. And in each of the intervals, we can actually calculate what will happen. And in this one, we have to do something. So what we do for the filters? The filters are, you can consider them functional. That's probably too mathematical to say, but consider this lambda case to be weights. So if we have the signal, we consider a specific interval, and we want to have weights which for everything in which k and j's are different to have that this sum is 0. So that means to have the expected value 0 when you apply this filter to any other element, any other mode than the one you consider. And then we want the conservation of counts, which means that the sum of all the lambdas should be 1. And in order to maintain stability, we need to make as small lambdas as possible. So that means that we have to minimize the sum of the squares. So this is the least square minimization. And then after that, we receive some numbers, which unfortunately could be negative. I'll show you that in a minute. But we have to do constraint classification of these results, in which we say, okay, if we receive a number which is less than 0, we have it at 0, and all the others to reassemble them and to make them integers. So what we do in this procedure, because I don't have any slide for it, we just say, okay, we have to estimate what are the non-negative integers which corresponds to each of the atoms which are present in the intervals. Or the baseline. And we consider different numbers. They have to sum to the total number. But at the same time, we want to make them integers. These filters will give us non-integer values. We underestimate a little bit, and then we have a priority queue in which say which one is going first. The good thing is that we can do the feedback after the tomographic reconstruction to change the priority queue and to improve the results. But okay, let me show some pictures now. These are the modes. The modes is just the normalized functions. So the peaks which you consider here, so they were kind of to have the sum to sum up to the combined spectrum. here we kind of make them, each one to have the same height, to have the same sum, to sum to 1. And then we have different situations, and based on this, we calculate different filters. And these filters have, this is the 0 line. It has some negative values, so that sometimes we, because of the stochastic way of receiving the data, we could have some of them negative. And this is for the other 8. This is a total of 8 intervals. So after applying that, we receive these are the element maps. This is the combined results for all this. I call it standard method, but we have some improvements of the standard method. You probably on this view, you cannot say much difference between it. The only difference is the copper. You can see how much noisy is that with the standard method. But also I can assure you that we have a little bit better understanding, better results for the other filters because we were able to do the tomography. So a few words about the tomography. So what is the tomographic reconstruction? Probably if you studied the tomographic reconstruction, you know that how to do it with Fourier transform and back projection. Actually, if you're in RISE, you probably shouldn't do that because people know a lot about constraint minimization. So what is important to see, if you have the electron beam, so you can say that depending on the intersection of the electron beam with the voxels, you can actually have some weight here, and this C is the concentrations in the voxels. So you subdivide everything into relatively small voxels. For each of the voxels, you have a concentration, and then you have that actually the result should be something like this. So these mu's are known, and the C's are unknown. And then what you do, you say, okay, I'm solving this minimization problem. This is the fitting of the data. This is the data you have received. This is the unknown C's with the known coefficients here. And then you put something which is called total variation minimization. That means the nearby voxels, they shouldn't differ, the concentration shouldn't differ by much. And if they differ, we want this difference to be as small as possible. And that goes to, so we want to minimize this lambda is some coefficient to match that these sums are all almost. So I said that you can see this is the software you're using, which is by Toby, which is actually available also. It's originated from a PhD thesis from the Rice University, so that is good. And this is the results. This is the first result. I like it because Toby made really good colors for this. This is aluminum, gallium, and titanium. And then I have several other pictures. This is a little bit different viewpoint. And keep in mind that here, when you are viewing a three-dimensional object, what you want to do is to make different transparency to see something. And this is probably the proper way to do it. The nitrogen is almost not visible because we set the transparency of the lower concentrations very light, so you cannot see anything. So this is another position, which is a little bit more of this, and then it is a little bit higher transparency in which you can see the nitrogen is actually have a pretty good concentration, low concentrations. And then what I'm very proud with, although material scientists, they don't like this picture at all. But this picture is only about the oxygen, because this is exactly a layer of between two different metals, and it turns out that this is oxygenated. This cannot be detected by the standard method. So we have detected, and actually you see that there are different concentrations and this kind of stuff, but you have to put the transparency on almost to zero to have a very opaque objects to actually view that. And these are two more things that I thank you very much for the attention.
Wow, fantastic. Thank you very much. We have time for one or two questions. So I'd like to go back to when you're generating the biorthogonal filters.
Yeah.
To a non-mathematician, how do I think about this? Like, I understand you're trying to minimize in a least squares way, but you get such complicated functions, they're better than just like simple Gaussians, right? To eliminate, like when you go to the next slide.
Yep. Okay.
Like they look like you're creating complexity out of nothing in some ways. And so
why it is out of nothing? Okay.
I'm saying it looks like it. So I'm wondering where do you get this complexity? Because it's not out of nothing, but it's coming from somewhere.
So this one here, this is the zero level.
Okay.
If you see this one here, this one, it's big where this could happen.
Yes.
And then you have that it is low probability if that happens. Here, eventually, this is very close to zero, but I don't know. This is just the mathematics. This is you calculate the orthogonality, and that gives you. I can suppress this one not to be positive, to be negative there, but it is kind of spread around. So that means if you have this something from this atom, it would be kind of eliminated. And that is why, and here it's obviously negative because this is where the baseline is coming. So you don't want to count anything which is coming from the baseline.
Okay.
So that is kind of makes sense. The thing is that the least square minimization is the reason is we want these coefficients as small as possible.
Mm-hmm.
I tried with some other things, which makes them bigger coefficients, and then it becomes unstable.
Okay.
Because we have very small quantities, and these small quantities the stability is the first thing you have in mind when you have small quantities. You don't want to have from some weird experiment because eventually they don't show up in the middle of the peak, they show a little bit off of the peak, and then you kind of cannot predict what is going on.
Okay.
Yep.
Any questions from the audience? Any questions from Zoom? No. All right, let's thank Peter again. And